Welcome back to the podcast, where we turn textbook algorithms into engaging, real-world conversations.
I'm absolutely thrilled you're joining us today because we're going to unpack one of the most foundational and honestly beautifully elegant algorithms in all of computer science. We're talking about insertion sort.
Ever wonder how computers take total chaos and actually sort it out? Think of your data like this messy, randomized deck of cards.
Yeah, how does an algorithm make sense of it?
The secret? It's called a sorted prefix.
Basically, keep the left side organized and leave the right side unprocessed. We kick things off with just one card, the ace. Boom, our organized prefix is established.
Next up, the algorithm grabs the 2. Since it's bigger, it goes perfectly right next to the ace. Then comes the 8.
Just like that, we're building up that nicely sorted prefix on the left side. But wait, look at the 5. The algorithm neatly tucks it right between the 2 and the 8.
Okay, so that's the golden rule here. The algorithm constantly ensures that the left side stays absolutely flawless. This unprocessed 8 is up next.
Notice how in every single pass, the sorted portion steadily grows, while the unsorted portion shrinks.
Basically, the algorithm is just systematically moving a boundary line from left to right across the data.
Every time it crosses a card or number, it pulls it into that sorted zone and shifts things around until that new number or card is perfectly placed.
The simple way to remember the algo logic is evaluate, shift, insert.
Okay, we got the short version to remember now. Give me the interview-ready answer.
Insertion sort works like sorting playing cards in your hand. It takes one element at a time and places it in the correct position within the already sorted part of the array.
Now let's decode the actual pseudocode for insertion sort. Don't worry, we're not just reading code. We're going to visualize what each line is doing.
Okay, so the first line says, insertion sort of R. That means we're giving the algorithm an array to sort, right?
Exactly. The array is our input. Then we calculate n, which is simply the length of the array.
So if the array has 5 elements, n is 5. Simple enough.
Next, the loop starts from I equals 1 and goes up to n minus 1. Why 1? Because we assume the first element is already sorted by itself.
So the sorted part starts with just one element? Then we pick the next element and place it correctly?
Yes, exactly. That picked element is called the key. So when we say key equals R of I, we are saying this is the value we want to insert.
And then J equals I minus 1. So J points to the element just before the key.
Yes, J helps us scan backward through the sorted part of the array. We compare previous elements with the key.
Now the while loop says, while J is greater than or equal to 0, and R of J is greater than key. What does that mean in plain English?
It means keep moving left as long as we haven't reached the beginning, and as long as the previous element is bigger than the key.
Oh, so if the previous element is bigger, it's in the wrong place. We need to shift it one step to the right.
Exactly. That's what R of J plus 1 equals R of J does. It copies the bigger element one position ahead.
So we're making space for the key? Like sliding cards to the right before inserting a new card.
Perfect. That's the whole idea. After shifting, we do J equals J minus 1 and continue checking the element before it.
And this keeps happening until we find a smaller element, or until J goes before the beginning of the array.
Yes, once the while loop stops, we know the correct position for the key. Then R of J plus 1 equals key places it exactly there. That's insertion sort in action. Pick a key, scan backward, shift bigger elements, and insert the key in the right place.
So the pseudocode is basically building a sorted section of the array, one element at a time.
Exactly. And that's why insertion sort feels like arranging playing cards in your hand. Simple idea, clean logic, and very interview-friendly. Now, let's dry run insertion sort with the array 5, 1, 4, 2, 8, 3. We are entering the loop for the first time.
So we start with the first element, 5, and we treat it as already sorted, right?
Exactly. At the beginning, the sorted part is just 5. Now the loop starts from index 1.
At index 1, the key is 1. So key equals 1, and J points to the element before it, which is 5.
Now we compare 5 with 1. Since 5 is greater than 1, 5 shifts one step to the right.
So the array temporarily looks like 5, 5, 4, 2, 8, 3. We made space for 1?
Yes, exactly. Then J moves left and goes out of range, so we place 1 at position 0.
Now the array becomes 1, 5, 4, 2, 8, 3.
Great, we are moving into second loop. The sorted part is now 1 and 5. Next, we move to index 2.
At index 2, the key is 4. J points to 5.
We compare 5 with 4. 5 is greater, so 5 shifts to the right. Temporarily, the array is like 1, 5, 5, 2, 8, 3.
Now we compare 1 with 4. 1 is smaller, so we stop shifting?
Correct. 4 belongs after 1 and before 5, so we insert 4 at J plus 1.
The array is now 1, 4, 5, 2, 8, 3.
Awesome! We are getting into third loop. Nice. Now the sorted part is 1, 4, 5. Let's move to index 3.
At index 3, the key is 2. J points to 5.
5 is greater than 2, so 5 shifts right. Now J moves to 4. So temporarily, the array is 1, 4, 5, 5, 8, 3.
4 is also greater than 2, so 4 shifts right too. So the transitional array is 1, 4, 4, 5, 8, 3.
And now J points to 1. 1 is not greater than 2, so we stop.
Now we insert 2 after 1. The array becomes 1, 2, 4, 5, 8, 3.
Entering into loop 4. Perfect. Notice what's happening. The left side is becoming more and more sorted after every pass.
Now we move to index 4. The key is 8, and J points to 5.
We compare 5 with 8. 5 is not greater than 8, so nothing shifts.
So 8 is already in the correct position? That was easy.
Exactly. We simply place 8 back where it already was. The array remains 1, 2, 4, 5, 8, 3. Now we enter into loop 5.
Now we move to the last element. At index 5, the key is 3.
J points to 8. 8 is greater than 3, so 8 shifts right.
Then J points to 5. 5 is also greater than 3, so 5 shifts right.
Now J points to 4. 4 is greater than 3 too, so 4 shifts right.
And then J points to 2. 2 is smaller than 3, so we stop shifting?
Exactly. 3 belongs after 2 and before 4, so we insert 3 at J plus 1.
And now the array becomes 1, 2, 3, 4, 5, 8.
That's the full dry run of insertion sort. Each time, we pick a key, move bigger elements to the right, and insert the key in the correct position.
So for the array 5, 1, 4, 2, 8, 3. Insertion sort gradually builds the sorted section from left to right.
Exactly, and by the end, the array is fully sorted. 1, 2, 3, 4, 5, 8.
And that's a wrap on simple insertion sort. It's one of those algorithms that looks simple on the surface, but teaches some incredibly important concepts about sorting, shifting, and building solutions step by step.
Absolutely. If you understand why elements are shifted instead of swapped, and how the sorted portion grows after every pass, you've already mastered the core idea behind insertion sort.
Before we go, let's do a quick interview lightning round. 3 questions that almost always show up.
Question number 1. How does simple insertion sort work?
Easy. It maintains a sorted portion of the array. In each pass, it picks the next unsorted element, shifts all larger elements one position to the right, and inserts the element into its correct position.
Question number 2. What's the time complexity of insertion sort? I know this one catches a lot of people.
The answer is, best case is O of n, when the array is already sorted. Average and worst cases are O of n squared, because elements may need to be compared and shifted multiple times.
And finally, the classic interview favorite, is insertion sort stable and in place?
Yes, it's both. It's stable because equal elements keep their original relative order, and it's in place because it sorts the array using only O of 1 extra space.
Those 3 questions alone can earn you some serious interview points. And if you can explain them with confidence, and maybe even walk through a quick example, you'll stand out from the crowd.
Remember, interviews aren't just about writing code. They're about explaining your thought process. If you can clearly describe what the algorithm does, why it works, and when you would use it, you're already thinking like a great engineer.
In our next episode, we'll level things up by exploring binary insertion sort and see how binary search makes finding the insertion position faster, while uncovering why the overall time complexity still stays the same.
Enjoyed the episode? Like, subscribe, and turn on notifications so you never miss a new video. Thanks for watching!